Hello, my name is Father Jonathan Munn. Now, normally I am a priest, but I'm also a mathematician. I thought what I'd like to do is to do some mathematics rather than anything theological, because I enjoy mathematics very, very much. And I enjoy teaching mathematics wherever I can. So I want to make a little channel that's actually independent of my work on theology, so that I can share some mathematics with you. Now, I thought what I'd like to do today is I'd like to look at the idea of triangles and squares. And you can ask yourself, well, that sounds very boring. Um, but I can say, well, I'm going to ask a silly question. When is a triangle a square? And, well, that sounds even sillier question. Triangles have three sides, squares have four sides. Ah, but then perhaps I'll nail it down a bit. Let's look at that. One, one, two, three. One, two, three, four, five, six. So what have we got here? We've got triangular numbers. Triangular numbers have an interesting property. Let's let n Tn be the nth triangular number. And you might know the formula for this. The formula for this, of course, is that Tn, the nth triangular number, is half of n times n plus 1. And if you've done any work on arithmetic progressions, that should be quite obvious. Um, Essentially, the idea of proving that is to think about putting two triangles together and getting a rectangle. And if you do that, you get a rectangle of length n and width n plus 1. Put them together, so you multiply them together, so that's n times n plus 1. But a triangle is half of that, so is the particular answer there. So now, the question is, this is a question I want to ask. When is a triangle number a square? So what does that mean? Means find m and n, which are natural numbers. So essentially what I'm saying is they are counting numbers, 1, 2, 3, etc., etc. That's what that strange looking n is. So that, oh, what do I want? I want m squared equals Tn. Well, that is a half n plus 1. So you can see, that's what I'm asking you to look at here, is that what we have here is our triangular number here being square. So that's essentially what I'm saying. When is a triangular number square? Now, how do I proceed with that? Notice I've got a limitation. The limitation is that m and n have to be positive integers. They have to be 1, 2, 3, 4, etc. And this, what you see here, is it makes it a little bit more tricky because of that restriction. So what I'm going to do is I'm going to transform that equation a little bit better, and so it makes it a little bit more obvious. And what I'm going to do is essentially I'm going to make a transformation. I'm going to put this let's put m equal to y over 2 and n equal to x minus 1 over 2. So that necessarily means that y has got to be even and x has got to be odd. And I'll see that's important in a minute. We can encode that in quite happily. So that if I do that, well, what happens? Well, what happens is that I've got y over 2 squared, that's m, is equal to half times x minus 1 over 2, that's n, times x minus 1 over 2 plus 1. That's it again. And so now what I can do is I'm going to do a little bit of simplifying with that. And I can say that that's y squared over 4 is equal to, right, well, first of all, I've still got my 5 here. I've got x minus 1 over 2, that's another half here. And this other bracket I'm looking at here, well, what have I got? I've got this 2 here, well, it's 1 here. So that becomes, so 1 becomes 2 halves. And so if I put it together, what have I got? What have I got? X plus 1 over 2. And that simplifies quite nicely because I've now got an eighth of x minus 1 times x plus 1, and you recognise that as being a difference of 2 squares, x squared minus 1. So let's just do the multiplication. Multiply that. I've got x squared minus 2y squared equals 1. Remember, we've got x is odd and y is even. Now, the beauty of it is that equation there actually encodes it. Because, well, what do I know? I know that. What I can say is that if I look at this thing here, 2y squared is always going to be even, but this is odd. That means that x has got to be odd. So essentially encoded into our situation, we've encoded that x is an odd number, and therefore we will see that that means that y must be even when we come to do it. Now, also the next thing to notice is here, go back to black, is that if I can sort of factorize this, so I get 1 equals x minus root 2 y, oops, y, x plus y root 2, like so. And if x and y are integers, well, I've now got this root 2. Now, remember, root 2 is irrational. So if x and y are integers, and root 2 is irrational. So we know that x plus y root 2 is always irrational. If it weren't irrational, then root 2 would not be irrational. We know that it is. This sets us up quite nicely. What we now have here is that x plus y root 2 is a particular type of number. It's called an algebraic number. And it's called an algebraic number because it is an integer plus another integer times an irrational number. So we know what's causing the irrationality, it's root 2. Everything else is quite straightforward. Now, irrational numbers, the algebraic numbers are really very nice because what they can do is they behave just like normal numbers. Yeah, like if you multiply two algebraic numbers together, you get an algebraic number. They're closely related, if you know what complex numbers are. They're very closely related with complex numbers. So, for example, what we can do is we can try them Here's one algebraic number, and here's another algebraic number. So A, B, C, and D are integers. And if you multiply that out, you can break them off quite nicely. So you get that. Remember, that comes from multiplying B root 2 and D root 2. So you get that extra bit of root 2 coming through. Then you get BC plus AD root 2. So you know that AC plus 2BD, that's an integer, and BC plus AD is another integer. And so you've got two incorrect numbers multiplying together to give you an incorrect number. We've also got something rather nice with algebraic numbers. As I say, they're a bit like complex numbers in that they've got an obvious what's called conjugate. So what I can do here is if I now multiply this out, I'm going to multiply it by the conjugate. Well, what do I get? Well, again, it's difference of two squares. A squared minus 2b squared. Now that is an integer because a and b are integers. So this is the conjugate. Right? That's called the conjugate. And the beauty of this is if you multiply two numbers together and take the conjugate, you can do this yourself. This is a good little exercise. The conjugate of the product is the product of the conjugate. So if you basically what I'm saying is if you multiply two algebraic numbers together and then take the conjugate, well, that's the same thing as multiplying the conjugates in the first place. Now that's actually quite important for our situation here, because you see what I've got here is I've got the equation we've had x squared minus 2y squared equals 1. And what I can do is I can say that what that's essentially saying is that if I multiply the conjugate, multiply the conjugates of these two numbers, I get 1. And so that means if I now multiply, so if a squared minus 2b squared equals 1, then of course that's saying that a plus y, sorry, a plus b root 2 times a minus b root 2 is also equal to 1. Now, what do I know? Well, I've got, if I multiply x plus y root 2 with a plus b root 2, of course I get something a little bit, as I say, looks a bit complicated, but you understand that this is quite important and very useful. So that's a plus b root 2, a x plus 2yb plus a y plus bx times root 2. And that means that if, change colour, if this is a solution to this, and this is a solution to this, then this is a solution of, well, this is not horrible, but don't be don't be upset about this. This is what you've got here. It's spectacular. we now know that ax plus 2yb squared minus 2ay plus bx squared equals 1. What does that tell you? That tells you something like really nice. It means that if you have functions of x squared minus 2y squared equals 1, you can multiply them together and get a third, and get a fourth, get a fifth, and so on and so on. By multiplying, you've got a whole string of numbers that you can bring out. And well, I might talk about what this means a little bit later one day. This is actually related very much, it's related to the circle. There's triangles, squares, and circles in this little talk. Now, what does this mean? So, it means if I can find one solution, if I can find one triangle that's actually a square, then I can find an infinite number. Now, is it possible? Can I find um, a solution? Well, okay, let's do a little bit of fun. Let's see if we can find something. So if I've got, let's just do a few small values. 1, 2, 3, 4, 5, 6. And what I want to do is I want to look at x squared minus 1 and see if it's a double square. If it's twice a square. Right, so 1 squared minus, minus 1 is 0. Well, that would fit. I mean, you do have x squared minus 2, so that is, um, and that is a solution. The only trouble is, 1 plus 0 root 2, I try and square it, is 1 plus 0 root 2. It doesn't, we don't get anything from it. So it's actually quite it's what probably, it's probably an identity. It's an identity element. It means that when you multiply um, uh, your solution by this thing, it doesn't change. So it's not altogether helpful. Okay, so 2 squared minus 1 is 3. 2 squared is 4, minus 1 is 3. 3 squared minus 9, 3 squared is 9, minus 1 is 8. Oh, 8 is twice a square, it's 2 times 4. So what we have a solution. We do have a solution. So x, y is equal to 3, 2 is a solution of x squared minus 2y squared equals 1. So if I now say, well, let's let lambda equal to 3 plus 2 root 2. So that's our algebraic number, which is related to 3, 2. Then what I can do is I can square it. I've got lambda squared is equal to 17 plus 12 root 2. You can check that if you like. 3 squared is 9. 2 root 2 squared is 8. So 9 plus 8 is 17. 5 3 times 2 is 12. Actually, 2 is 12. So that gives me another solution. So I've already got another solution. 17 12. So 17 squared is going to be 89. 12 squared is 44. Twice 12 is 288. 189 288 equals. So there's another one. What about lambda cubed? That gives me, okay, that's a bit more tricky, but if you do the maths, I encourage you to do so. If you do that, it gets 12 to 70, 99 to 72. It works as another, that is another solution. Now you're going to say to me, well, hang on a minute. This is all very well, talking about x's and y's, but we're going to have to squares and squares and triangles. Yeah, let's go back. So we just have to remember that we were trying to solve m squared equals tn. That's what we're trying to solve. So i.e. that m squared is equal to half n times n plus 1. And I told you earlier what we were going to do is we're going to say that n will be x minus 1 over 2. And you notice all the x numbers are indeed odd, which is good. And m is going to be just simply y over 2. And you notice all the 1 numbers are missing, as we expected. So that's all we can do. We can say, right, let's look at our first situation. So if I've got, um, now we're going to look at this. I'm going to say, right, so we've got, if we've got solution x, y equals 3, 2. That means that n, m is equal to, okay, so n is x minus 1 over 2, 3 minus 1 over 2 is 1. And m rather, is y over 2, which is just 1. So that just tells me, you can just check this out, that 1 squared is equal to the first t, which is 1. So it works, that's nice. Okay, but it's a bit difficult. So let's go to our next solution. Well, what's our next solution? The next solution is 17 and 12. So I want x, y equals 17, 12. That means that n, m, yes, I'm writing it that way round, but you get the idea. So x minus 1 is 16 divided by 2 is 8. Y over 2 is 6. So let's just look at that. So what we've got p8 is equal to 1 plus 2 plus 3 plus 4 is equal to 36. Well, so that's interesting. That's 6 squared plus this. Okay, one more. X, y equals 99 and 70. So what about n and m? Well, that's 49. So 99 taken away 1 is 98, divided by 2 is 49. And 70 divided by 2 is 35. And I think, if memory serves, so we do this. So the 49th triangular number, get your brain in gear for this, is going to be it's going to be 1225, which is equal to 35 squared. So the beauty of this is we can now generate as many solutions as we like. What's not clear at the moment is whether all the solutions here are generated just by that little x being 3, 2 by lambda. That's something perhaps we need to look at later. How do we get all the solutions using this method? One little thing is the question is why the root 2? Well, I want to know why root 2. It's actually quite nice. Let's just put a triangle. Oops, that's a little higher. Just bring it down a bit. Yeah. Now, if I look at the root, a bit of sticky out there. So now what have we got? We've got a triangle, m plus 1 there, n there, and an h. And you know Pythagoras' theorem. We know that the area is half base times height. There's your again, bring it down. The area is half the base times the height. Now, what about the hypotenuse? Well, Pythagoras says that h squared equals to n squared plus n plus 1 squared, which you should know to be 2n squared plus 2n plus 1. And that means that h has got to be equal to the square root of that. 2n squared is 2n plus 1. Now, if I just take the n out of it, let's take the n out a bit. So I get 2 plus 2 over n plus 1 over n squared. So what we notice is, for large n, h is approximately n root 2. And that is gives you sort of geometric reason why the root 2 keeps popping up here, which I think is rather lovely. So that's a little presentation, little thought about triangles and squares. Perhaps one in the future talk, I can perhaps look at why there's a relationship between circles and squares. There's also a nice little relationship which we can look at also with the problem of doubling triangles. And I think that might be also a good talk later on. Thank you for watching. Hope you have a great day. Bye bye.